So today we are officially starting our new unit, applying characteristics and properties of three-dimensional figures to solve problems and justify solutions. Okay, so for today our essential question is, how do I tell the difference between different types of polyhedrons? So the main concepts that we're going to hit today, first one is kind of deciphering the difference between polyhedrons and non-polyhedrons. Looking at Euler's formula, bases versus lateral faces, and things on surface area and volume. Okay. Some of the things that we're going to use that you already know or should already know or have. One is the area formulas. Okay, when we're dealing with surface area and volume, right, we're going to be dealing with, you could almost say, an infinite number of cross sections, right, or slices of these shapes. Okay. So if you know how to find the surface or the area of each part, you should be able to find the surface area and or volume. Perimeter, circumference, height, and radius. These are all terms that we have used in the past and we will be using in this unit. Okay? I'd like you to take a moment and study those sets of shapes. Okay, I'm going to give you about 30 seconds to study them, and then I want you to decide what makes these polyhedrons and these not. Okay, 30 seconds starting now. All right, quickly share with your neighbor what you believe makes something a polyhedron. All right. A polyhedron is a figure with 4 or more polygons that intersect at the edges. Okay, a polyhedron has flat surfaces. So a pyramid, prism, those have flat sides, right? All the sides are flat. Whereas a cylinder, a cone, a sphere all have rounded faces or curved faces. And so those are not polyhedrons. Those are non-polyhedrons. So now let's look at something else. We want to look at kind of a difference between faces, vertices, and edges. Right? the way we define a face, right? A face is a flat surface of a polyhedron. Okay? A vertice is a point where three or more edges meet. And finally, edges are the segments where two faces intersect. Okay, or meet. And we're able to, thanks to Euler, or Euler, we were able to find, we're able to actually calculate. If we know two of these, we can find the third one. In his formula, he said that if I have if I have faces and I add vertices, the number of vertices to that, I get the number of edges plus 2. Okay? But now, remember, this is only for polyhedrons. Okay? It doesn't work always on non-polyhedrons. Sometimes it works, sometimes it doesn't. Okay? So, faces plus vertices is equal to edges plus 2. So if I had something with 6 faces and 6 vertices, that's 12. And minus 2, that means that edges would be 10. Yes, plus 2. No, edges plus 2. All right, so let's look at a type of polyhedron, something called a prism. Okay? Prisms are polyhedrons that almost looks like a G. Polyhedron with two congruent and parallel bases connected by lateral faces that are all parallelograms, sorry. Okay. Polyhedron with two congruent and parallel bases connected by lateral faces that are all parallelograms. So on this diagram, we can already see that, and I have this on your paper for you, that we already labeled the two bases. Okay, these are our bases. These are parallel, right? They are polygons. They can be any polygon, right? Two bases, polygons in parallel planes. Okay, you have two bases, and they are any polygon. So I could have trapezoids if I wanted to, or triangles, or hexagons, so long as they are both the same and congruent. In parallel planes, you can make a prism. Now, the other part of it is the lateral faces. And so the lateral faces are all these faces here. Okay? Lateral faces. And when we talk about surface area, we're going to be talking about lateral area and base area. Those are our two primary terms when we start talking about surface area and volume. And so to find the surface area, you need the lateral area. And so for that, you need to know what are your lateral faces. And so that's all these parallelograms here that connect our two bases. Okay, and then we have lateral edges. Okay, lateral edges. So again, bases, these can be any polygon. Okay, there's two congruent polygons. In parallel planes. Okay, the faces, right? Those are those lateral faces. And for a prism, they're all parallelograms, or in what we're going to be dealing with, rectangles. Okay, they're all rectangles. And remember that our height is always perpendicular to the base. Or in this case, the bases. Okay? So our bases, right, are the two ends. Then we have the lateral faces. They're all rectangles. And our height is always going to be a term that is perpendicular to our base, or bases. The next type of polyhedron is called a pyramid. Okay? And a pyramid is a polyhedron with one polygon base and lateral faces made up of triangles that all meet at a point called the apex. Okay. So for the definition of pyramid up at the top, okay? Polyhedron with one polygon base and lateral faces made up of triangles that all meet at a point called the apex. You can kind of see in that diagram there where I'm pointing to for the apex. So when we're dealing with pyramids, we want to know a few things about them and where we can find information. Base. The base is a polygon. Okay, a polygon. It is this shape down here that is perpendicular to the height. Even if it itself is a triangle, right, it is opposite, the base is always opposite of the apex. And our core concept, again, is that the pyramid is named after the base. Okay, so if we have a square, then it's a square pyramid. If it's a rectangle, it's a rectangular pyramid. If it's a triangle, it's a triangular pyramid. If it's a pentagon, it's a pentagonal pyramid. Perimeter is the distance around the base. Okay, we're just finding that distance of that base polygon, and we're going to use that next class to be able to find, to help us find the surface area. Okay, slant height. Well, slant height is on a pyramid. Slant height on a pyramid is the length from the apex to the midpoint of a side. Okay, it's perpendicular. Okay. That slant height is basically the apothem of a lateral face. I want to know that length from the apex down to the midpoint of that side. And it's perpendicular. It is not that other length. It is not that other slant. It is not this one. Okay? This over here is not the slant. Okay? This blue one is. The height of this is from the apex to the base, perpendicular. Okay, so distance from the apex perpendicular to the base. So this would be our height. Alright, so let's talk about the shapes that are not polyhedrons that we're going to focus on. The three non-polyhedrons are cones, cylinders, and spheres. Okay. So I'm going to label, I wrote these in there on your guys' notes. You're here in class, so I'm going to label these. For a cone, just like a pyramid, the point at the top is our apex. The circle at the bottom, or that is perpendicular to the height, that is our base. Okay. Our height is, of course, perpendicular to our base. The definition of a cone is a 3D shape, a 3D figure that tapers smoothly from a flat base to a point called the apex. Okay, that point is the apex. A cylinder is, this one actually is one of the hardest ones to find, is a 3D shape that has two circular bases and a cylindrical surface, lateral surface between them. Okay, a 3D shape that has two cylindrical bases. So this is one of my bases. That's my other base. And it basically has one face. One face. One lateral face. And that's that pop can that if you take the top and the bottom off and you cut it down the middle and flatten it out, you're going to have a rectangle, basically. And then a sphere. A sphere is a perfectly round 3D figure. As Sphereus said in Flatland, I am the perfect circle. Right? Most perfect circle because it is an infinite number of circles stacked on top of each other. Okay, perfectly round 3D figure. It has no edges, no vertices, and a face. Okay, so if we think about our thing there, if it doesn't have any edges, doesn't have any vertices, it only really has one face, that doesn't work for our formula. Right? Because 1 plus 0 is 1, and then that would mean our edges is -1. And you can't have a -1 of things. So that's an example of where the Euler's formula doesn't work. For spheres, spheres do not have what's called a lateral surface. So no lateral surface. Okay? No lateral surface. A cylinder has lateral surface. A cone has lateral surface. Right? But a sphere does not. So regular polyhedrons, okay? These are called Platonic solids after the philosopher, mathematician, and scientist Plato. Okay? They use, just like polygons, they use Latin in their names. So we have tetra, which is 4. And my ends disappeared. Okay. Tetra is 4, so this is 4 faces. Hex, that's still the same, so that's 6. 6 faces. Hexahedron is also labeled as a cube. Oct. Oct is 8. So that has 8 faces. The faces on this are of equilateral triangles. Okay, so that's an equilateral. For hex, that was squares. 6 faces of squares. Tetrahedron is 4 faces of equilateral triangles. Dodec. We did that one as part of our warm-up. Dodec is Latin for 12. So I have 12 faces of pentagons. Okay? The other thing about Platonic solids is that at each vertice, they have the same, they're meeting the same number of polygons. So if I pick this vertice right here, that is a meeting of 3 polygons. And so at every vertice in this, it will be a meeting of 3 polygons. Okay? And then icosa. This is another one that's icose, slightly different than polygons. Normally, when we would have a polygon with this number of sides, we would just call it a 20gon. And in this case, we actually use the Latin for 20, which is icose. So icosahedron is 20 faces of equilateral triangles. Okay. So using equilateral triangles, we're able to get a icosahedron. And so that's 20 faces. Dodeca was 12. Hexahedron, right? We did that one slightly during warm-up. It has 6 faces, has 8 vertices. How many edges would it have? 6 plus 8 is 14, minus 2, 12, right? Octahedron, right? So vertices, we have 1, 2, 3, 4, 5, 6. So we have 8 faces, 6 vertices again, which means we have a 6 and an 8 again, just different order, which means edges are going to be 12 again, even though they're different shapes. Octahedron and hexahedron both have the same number of edges. Okay? Dodecahedron, right? Well, we have for faces, we have 12. Vertices, there's 5 there. And we have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, there should be 1. Yeah, 20 faces, 20 vertices. Hey, that's pretty accurate. 20 vertices, maybe for a dodecagon, or dodecahedron, sorry. So how many edges would it have? It has 12 faces, 20 vertices. It would have 30 edges. That quick. Yeah, nice job. Icosahedron, right? We have 20 faces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like 12 edges. 12 vertices. Icosahedron, 20 faces, 12 vertices. Again, it's going to have how many edges? 30. So dodecahedron and icosahedron both have the same number of edges.